In this training series on power system studies using MiPower software, we are covering transient stability in this presentation. Transient stability is the ability of power system to return to normal state or stable operating state when there is a sudden and large disturbance. The disturbance can be transmission line faults, sudden load changes, loss of generation, line switching, etc. For conducting transient stability on a power system network, we need database, the MDB file. The inputs for conducting transient stability study are the network parameters like bus voltage levels, transmission line parameters, transformer parameters, motor data, etc. Generator scheduling, the modeling of generator, then the load schedule, then AVR and governor data if they are present in the system. The outputs from the transient stability study are the machine voltage, magnitude and its angle, then frequency of machine, the real power, reactive power, mechanical power, and field voltage or slip. Also, the transient stability study will give the bus voltage, the current through the lines, the impedance of the lines, and power flow through the lines. It will also give the maximum rotor angle of machine. Now, for the transient stability, we can simulate stability study with different types of disturbances. The disturbances include change in transformer parameters, change in transmission line parameters, change in load data, three-phase to ground fault, single line to ground fault, line-to-line fault, double line to ground fault, change in number of generator sets, total generator outage, loss of excitation, change in load model, motor starting or motor stopping, change in AVR voltage reference, change in real power reference, change in speed reference, etc. The different reporting options in transient stability are the standard report and HTML report. Now we will consider the case study. For the power plant considered, perform stability study using classical machine model or constant voltage behind ST dash. Then subtransient model with AVR type 1 and steam turbine governor type 1. Determine the maximum rotor angle swing with reference to the grid bus if three-phase dead short circuit occurs at the grid bus and the fault is cleared in 0.1 second. Use constant impedance model, grid inertia constant as 1000 seconds, solution time step of 0.02 seconds and simulation time of 3 seconds. Also determine the critical clearing time for the faulted grid bus. So this is the network which we have considered for conducting load flow analysis. We will consider the same system for transient stability analysis. Now here we are given the grid inertia constant. To enter grid inertia constant, we have to double click on the grid. We have to go to the generator library. Here we can enter the inertia constant 1000. Click on save button and then close. Click on save button in the generator data. We have to run load flow analysis to get initial conditions. So click on solve load flow analysis. Click on study info. After giving case number and case name, the slack bus is grid bus. Click OK, execute. Click on close. Click on plot load flow analysis. Click OK. We'll get the bus voltages. Now to conduct transient stability with constant voltage behind XT dash or infinite bus modeling, we have to double click on the generator. We have to select the model type as infinite bus modeling and then click on save button. Now we can conduct the transient stability by clicking on solve transient stability, give a case number and case name, and then click on study info. Select the load type as constant impedance type. String bus. String bus is the grid bus. Double click on the grid bus. Close. We have to enter the simulation time, end time, and step. We are given the simulation time 3 seconds and the step 0.02 seconds. Now we have to add the buses for plotting the graph. So we have to click on this add button. Double click on the buses. Bus number 1, 2, 3, 4. Whichever buses we need to consider for plotting the graph, we'll have to select accordingly. So here I have selected all buses. Then we have to select the disturbance. The disturbance is a 3-phase to ground fault. We have to click on this button to enter the disturbance information. So we have to select the fault on bus number 1 from this list. The disturbance starting time is 0 and the clearing time is 0.1 second. Then click OK. Now select the machine type as constant voltage behind XT dash and then click OK. Execute. Click on graph. Select machine. Click OK. Now for x-axis, double click on time in seconds, and for setting y-axis, double click on swing curve and then click on plot. So here we can see the maximum rotor angle swing with respect to the grid bus. The maximum rotor angle is 42.85. The stability of machine can be determined using the swing curve. Since the maximum rotor angle is less than 180 degree, the machine is stable for the clearing time of 0.1 second. Similarly, we can plot the machine terminal voltage by deselecting the swing curve and then double click on the machine terminal voltage and then click on plot. It will plot the machine terminal voltage. We can see the swing in the voltage graph. Now, initial voltage was 1.0 and the voltage has been reduced to 0.49 per unit, and then after a clearing time of 0.1 second the voltage has gone up, but due to the disturbance of 3-phase to ground fault there is a swing in the voltage graph. Now we can plot the frequency by deselecting the terminal voltage and double clicking on the machine frequency. Then click on plot. We can see the frequency plot. Now here the frequency is fluctuating between 50.43 and 49.58. We have not connected any governor or AVR. From the frequency graph, we can get the time taken for completing one cycle. Now to find the critical clearing time, we can click on solve, select transient stability, click on study info, double click on this disturbance, increase the clearing time to 0.4, click OK, then click OK here also, click on execute, click on graph, select machine and then click OK. Then double click on time in seconds for x-axis, double click on swing curve for y-axis and then click on plot. So we can see that for the fault clearing of 0.4 second, the machine is unstable. Now we'll change the clearing time to 0.3. Click OK. Click OK here also. Click on execute. Then click on graph, select machine, click OK. select time in seconds for x-axis and machine sync curve for y-axis. Click on plot. Here the maximum rotor angle with respect to the grid bus is 130.07, which is less than 180. So the machine is stable. Now we will change the clearing time to 0.32 seconds and then click OK. Click OK here. Click on execute and then click on graph, select machine, click OK. We will plot the sync curve again. On x-axis time in seconds, y-axis sync curve, click on plot. The machine is unstable. So the machine is unstable for a clearing time of 0.32 seconds. Now we will decrease the time to 0.31 second and then click OK. Then click OK here also. Click on execute. Click on graph, select machine, click OK. Select the x-axis time in seconds, y-axis machine sync curve, then click on plot. Here we can see that the maximum rotor angle has exceeded 180 degree. So the machine is unstable in this case also. So the just stable clearing time is 0.3 second and just unstable clearing time is 0.31 second for this network. Now we will do the second case study. The second case study is the transient stability with subtransient model with AVR type 1 and steam turbine governor type 1. For that, we have to double click on the generator, select subtransient modeling, and then here select AVR type 1. To see the AVR type 1 control block schematics, you have to click on AVR library and then click on control block schematics. This is the control block schematic of AVR type 1. And the value of the parameters are available here. And click on save button, close. Now the governor is steam turbine governor type 1. So we have to select type 1. We have to go to turbine governor library. We have to select type 1 steam from the list. You can see different types of governors available like steam, hydro, gas, etc. To see the control block schematics, we have to click on control block schematics. We can see the type 1 governor control block schematic. Now, these are the values of the parameters of type 1 steam turbine governor. Then click on save, close, click on save button. Now we are going to conduct the transient stability with the subtransient modeling of the machine. So click on solve, select transient stability, click on study info. The clearing time is 0.1 second, then click OK. Now to model the machine as subtransient model, we have to uncheck this machine type, and then to include the AVR and governor, we have to select AVR and governor, then click OK, and then click on execute, then click on graph, select machine, click OK. X-axis, double click on time in seconds. For y-axis, double click on machine terminal voltage and then click on plot. So here we can observe that the swing-in machine terminal voltage has been reduced after connecting AVR. Similarly, we can plot the swing curve by setting machine swing curve on y-axis. Click on plot. Now we can see that the maximum rotor angle is 91.23 with respect to the grid bus for a for clearing of 0.1 second after connecting AVR and governor. The machine is stable. Now we can increase the simulation time to 10 seconds and check the graph. Click on execute. Click on graph, select machine to plot the parameters related to machine. For x-axis, double click on time in seconds. For y-axis, double click on machine terminal voltage and then click on plot. Here we can observe that the voltage is becoming steady. Now we can plot frequency of the machine by double clicking on the frequency. Click on plot. Here we can observe that the frequency is getting stabilized to 50 Hz. For the system we have considered, we have two transmission lines. What will happen when one transmission line is thrown off? What will happen to the current in the other line? We will observe that using load flow study and transient stability study. Now to observe the current behavior in the line using transient stability study, we have to click on solve, select transient stability, click on study info. We need to add the disturbance change in transmission line parameters and then click on this button, select the line. We have to select the second line because we are going to open the second line. The disturbance starting time is 0.1 second. The actual parameters of the lines are shown here and the number of circuit is 1. Now we are going to open this line. We have to click on compute. Existing number of circuit is 1, new number of circuit is 0. Then click OK. Now we can see that impedance has been updated after opening the line. Now here there are two disturbances. The first disturbance is a 3-phase to ground fault at grid bus. The fault is cleared at 0.1 second. And the second disturbance is the opening of the line at 0.1 second. And then click OK here. Click on execute. Click on graph. Select line to plot the current through the line connected between bus number 1 and 2. Click OK. Select x-axis as time in seconds, y-axis the current through the line between 1 and 2. Click on plot. You can see the current through the line is 462 ampere. Now the current through the second line is 0. We can compare the results of transient stability with load flow analysis. We need to open this second line. Select that line, right click, select element status as open. Then create a contingency. Click on configure, save contingency. Give a contingency name, line, open. Give a contingency number 1. Click OK. So the contingency has been updated now. Solve load flow analysis. Just click on execute and then click on plot. Select load flow analysis. Select the flow unit as ampere angle and then click OK. Now we can observe that the current in the line which is in service is around 462 ampere. Concluding, we have learned how to do transient stability using MiPower, configuration settings and features in transient stability. Also, we have seen the different report options. Thank you.